AutoCAD, and I said that that was what I was going to spend my next video on, was going to be my next streaming me working on AutoCAD, so it was a lie. What I'm going to do instead is I think I'm going to go through the chapter review questions. So we've already done chapter 2 review questions, but maybe that might not be a bad place for us to start. And well, it looks like chapter 3 review questions. So we have already done chapter 2 review questions. I won't give definitive answers or anything like that, but I think it's as good a place as any to revision. Now, for the questions that require, should be right here. Landscape products, materials. Yes, I've gone too far. These are the questions. Cool. If I was smarter, I would have had this ready before I got started. Okay, so the reason why I won't go through the mathematical questions is because I've already done that on my YouTube channel. So they've got work solutions, and that's probably way more useful than me trying to go through them now without a whiteboard or any other tools. So what I'm going to talk about is just read through these questions, and I'll talk about what I think about these questions. I will just start off by saying that with any of these questions, that obviously Copeland's been doing this a lot longer than I have, so take whatever, any of my criticism, especially if it's a criticism, with a grain of salt, because he just knows more than me, or has been doing this a lot longer than me, and he probably has a really good reason for all of the things that he's chosen to put in here. Though that said, getting my perspective, if I'm going to write 3 exams for you in the near future, it maybe isn't worthwhile. It isn't such a bad thing to know what I think about things. Okay, I am just trying to get to my groups, and you can't see that because I'm doing it in a different window. What I want to do is I want to just find files, and I'm going to try and find clues to prelim reviews. So if you're looking at my Facebook group, you should be looking for clues to prelim reviews, which is the document we're looking at here. And this doesn't give you the full answers. I do actually have full answers for all of these, but it's probably better for us to look at the clues, because by doing that, it gives us the page numbers where we're going to find our answers. I do have complete answers, which I will I'll also open up. If I had been a little bit more organized, sorry for the delay. Hey again in the chat. Yeah, don't donate. That would just make my life more difficult. I appreciate the sentiment. It's a much funnier joke to say than it is to do in reality. So I'm giving you the thumbs up symbol here, but yeah. Titanium. So I might not have posted all the prelim review answers for you guys yet. So I'm going to go to my other class and just look at if I've got the answers for titanium. Okay, so that's for titanium. I want to look at for scandium. I should have all of them here. Prelim chapter 1 notes, past prelims. Yeah, I should have given answers before that. Here we go. So what you'll see is a document here that says answers to prelim review part 2, and so I'm going to get that, and I'll post I'll get the third one while I'm here as well. So this is where I've gone through, and I've done for year 11. I've gone and typed up the answers for all of these questions, and hopefully that's of some value to someone. And we'll go through those together now. So we're doing chapter 2 now, and we'll bring those in as and when we need them. I'll keep them open because I have lots of room space, lots of screen space on this computer. I will just bring them in when we need them. Okay, so to start off with, keep in mind that we're doing chapter 2 questions. So chapter 2 should already be done for homework at this point. So, no, I did need to have OBS open. Okay. My brother's playing Civilization 6. So, the modern engineer is a multi-talented acting as designer, manager, problem solver, and communicator. Choose a large engineering project and discuss the roles that engineers have played in the various aspects of the project. Now, I made you do an answer thing. Well, my current year 11s, I made them answer a question talking about the role, how engineers has acted as manager, problem solver, and communicator in our Google Classroom. But this is talking about something different to what the homework I said. It says it was a large-scale engineering project. Now, in terms of answers, I have... chapter 1. No, I want chapter 2. Okay, Sydney Harbour... So the answers are the same for both here. Between my clues and my actual answers, they're the same. So we'll bring in here and what we've got. So the simple answer that I've got is we could talk about Sydney Harbour Bridge. That's the go-to. We have, for those of you who, I don't know if you would have watched the videos with Mr. Zeech in engineering in junior school, but it's possible. We have a video on Sydney Harbour Bridge. And so in that project, we had roles included client consultation, determining expected forces, calculating structural requirements, producing design drawings, reading design drawings, construction planning, time and financial and resource management, construction supervision, including site safety, quality assurance, that means making sure that everything is done to the specified standard, that things are in the right spot, and consultation with stakeholders and the media. I have some other ones. So the Snowy Hydro scheme, the Snowy Mountain scheme, is the biggest engineering project in Australian history. There's an argument that the NBN may actually be bigger, but I think it's safe to say that these two are the biggest two. And then a third major engineering project is cochlear implants. I'm not going to read out those answers. I'm going to assume that you can read just as well as you can listen. But that's where we're going to leave that question. So, it does say discuss. Now, discuss means you probably need to write a little bit more detail in a HSC question, and you really got to look at the number of marks. So what we did was we just identified a whole lot of things. For discussion, what you would probably want to do is you would actually want to expand on one of these. And let's have a look at the... you might want to say, so engineers would consult with clients to make sure that the client's needs were met. In this case, the client would be the New South Wales State Government. Determining the expected forces. So this would be considering things like wind forces, the self-load of the concrete and how many vehicles we're going to travel. Calculating structural requirements. So in that case, we're talking about determining how much steel is required to meet those forces. Then we'd have production design drawings. So production design drawings would be producing the layout for the steel, where things are going to go. And these days, a modern bridge would have a whole bunch of services that are running over it as well, which the Sydney Harbour Bridge does have. I don't know if it did have in the 30s, if there were traffic lights or anything like that on the bridge. Reading design drawings is an important part of being an engineer, being able to interpret drawings. Construction planning, so managing time, managing the budget, and managing resources, making sure that we have enough people on the project at all times, making sure that we're meeting our deadlines, and if we're not, we then have to let our bosses know and say, well, we're not meeting our deadlines, and trying to identify why we're not meeting those deadlines. If it's something that we can change to improve, then we do that. If it's something that's outside of our control, then what we do is we go to the client and explain to them, and hopefully the contract will have provision for variations that we couldn't have reasonably determined. My friend Disco, that's pretty much what he does for a living, is he works on disputes between engineering clients and engineering firms, so construction companies mostly. That'll be enough. I mean, the biggest question in the HSC these days is 6 marks. So it's very rare that you're going to have a question that's more than 6 marks. It's unlikely that you're going to get a question that's more than 6 marks. A 4-mark question is a very long question. So that answer is obviously big enough for 4. We've explained 4 things in detail. There may be a provision that a marker might give you additional marks for just listing 8 things. They might give you 3 out of 4 if you list a lot of things. Okay, compare 2 mowers and comment on the likely materials used to manufacture them each. How has this changed over time? Okay, so what we'll do is we'll just bring in the answers, and if someone wants to look at the answers, then that's fine. I mean, this is homework that's already been set and marked at this point. The Faraday push mower is a mower from 1830. The push mower was made from wrought iron and cast iron, and it improved on the scythe and sickle. So this is a scythe. What the Grim Reaper carries is a scythe. I'm sure in class I would have shown you a video of 11 in Anna Karenina when he's bringing in the harvest with the scythe. A sickle is what you use for a garden. So if anyone's ever seen Asterix and Obelisks, the druid always carries a sickle, but it's more famously now known for the symbol of communism. Made possible due to the... Okay, so this mower in the 1830s was made possible because of the increase in iron production during the Industrial Revolution. Okay, it's got some other comments there, but you can read them or not. The Royal in 1936 was petrol powered and made from cast iron with a steel frame and panels. It was made possible due to the increased use of petrol engines and steel production during World War I. And I have a couple of others that you can mention here that it's fine to use either of those. Pressed steel mower decks are cheaper than die-cast aluminium. However, aluminium is lighter. Okay, so let's have a look at here. Discuss the advantages of pressed mild steel decks and die-cast aluminium. Yep, steel is cheap and strong. And now, you can't really write cheap and strong in an exam. What you need to write instead is you need to say that steel is a very abundant material that is easily and cost-effectively sourced and manufactured. Has low manufacturing costs, would probably be a better answer. However, it is subject to corrosion, and aluminium is very light and not subject to corrosion. And it is also has relatively low production and manufacture costs. The Honda is shown in this chapter. It has no throttle control nor choke control. It is automatic. How is this done, and how could this be achieved? I'm worried I just lost my other document. So I'm just going to find that window. Yeah, I did lose it. So I'm going to make this a little bit wider so I don't lose the document when I click on things. Okay, so the Honda had computerized fuel injection, which replaces throttle control. We talked a little bit about this in class. I don't know if we really discussed it in any greater detail. So the idea would be that Copeland expects you to Google this to research why you wouldn't have the case. Computerized fuel injection and does this automatically, making it both easier and more efficient. So you don't need the blue section. That's just to add a little bit more context, and by all means you can go back and look at that later. Explain the 4-stroke operation of diesel and petrol engines in contrast the key differences between them. Well, we should know that the 4 strokes are suck, squeeze, bang, blow, better known as, or more formally known as intake, compression, combustion, which has other names, and exhaust. This is essentially the same for both diesel and for petrol engines, but the difference is that petrol engines need a spark plug, whereas diesel doesn't. It's just the temperature and pressure is high enough that it combusts spontaneously. Okay, so 6. Why is the 4-stroke more desirable than a 2-stroke mower in terms of environmental impact? Okay, so 4-stroke motors are more efficient. Let's see, 6. They 2-stroke mowers. So this answer here maybe leaves a little bit to be desired. I mean, I wrote it, but you need to specify 2-stroke mowers use more fuel, so that's a resource depletion. That's bad, right? We don't want to run out of stuff. and there is more exhaust, and exhaust contains more uncombusted fuel, so there's more pollution and CO2 emissions. Okay, so 7, conduct research into a two-stroke diesel cycle and explain how it operates. Why is this used for some mowers? Okay, so two-stroke engine is very similar, except that the two downstrokes, intake and combustion, are combined, and the two upstrokes are also combined. They are much simpler machines, they're lighter and they're easier to service, but they're much less efficient. And I've got a video there that you can look at if you want to see two-stroke mowers. Right? But we're not going to go into that now. Okay. Explain why diesel engines have become more popular in cars in recent years. So I would say diesel motors have definitely taken a not for diesel mowers. Yeah, okay, that's maybe fair. I was going to say diesel cars are not more common, but not anymore, because electric vehicles and hybrid vehicles are much more common. But for heavy vehicles, we still want diesel. Yeah, no, question 8 is what we're up to. Diesel engines are more fuel efficient, they're cheaper to run, and they're less polluting. Also, diesel engines need less maintenance than petrol engines. Why do they need less maintenance? Well, because they don't have all these explosions of the spark plug, they have produced less wear on the engine, from my understanding. And that's why they're more popular with heavy vehicles. If you have a 18-wheeler B-double or something like that, then you want to reduce maintenance. Maintenance is a real killer. Okay, question 9. Why, while not creating carbon monoxide, diesel engines have been challenged by nitrogen oxides and particle emissions. How have designers addressed these emissions? Okay, now we talked about this in class, certainly in the big class we talked about this. What we use is a selective catalyst reduction, and you can see that you can find notes on page 46 to look at that. Okay, question 10. It says, name and describe 3 types of forces. Kind of silly question. So what they're looking for, the answers are that they are looking for concurrent forces, collinear forces, and non-concurrent forces. That's probably what they're looking for. For me, though, that question is vague enough that people could say electromagnetic force, gravity, the weak force, and the strong force, right? They're pretty zany responses. When I say that's zany, well, how would we find that? What we do is we go to media, and I go to my pictures, and we're in titanium, and so I have this post here in Facebook, and it talks about what is a force. It talks a little bit about those 4 forces that we've mentioned, like sort of talking about quantum level. What is a force, push, pull, or twist is the term that we typically use. Oh no, it's a different picture that I have where I talk about quantum forces and things, which is surely love is the greatest force of all. There's a gif of that. I haven't seen Bridgerton, but I'm pretty sure that's what that's from. And then the XKCD post. I've talked about these things in class. If not, you can have a look. I'm sure I've talked about them in my YouTube videos on forces. So let's go back to this. Outline the 4 methods of vector addition. Well, 4 methods? I would say there's graphical and analytical. But we have that written here. So 11, forces can be added either graphically or analytically. Look at me saying exactly the same thing. You can see the correct answers on page 48 and 49. Okay, for the rest of them, 12 to 13, well, we're not going to go through those. And the reason why is if I go to my YouTube channel, we'll see that I have already gone through these answers. So I wanted to make this slightly small. We'll do that. Anyway, okay, so here, where are we looking at? We have questions that say, things like Prelim Chapter 2, Question 16, Prelim Chapter 2, 13 and 14, Question 12, and Prelim 19 and 20. I'm pretty sure they're all here. You might take a second to find them, but I'm pretty sure they're all there. Okay, so we can skip through these, and 20, 21, 22, these are all done in 3/4 method questions. These ones. You don't care, you'll either find them or you won't. Okay, explain what dislocations are and how they make allow for easier deformation of metal. Okay, well, we're going to need pictures for this one. Oh, I mean, I do have the working out for those questions, but well, no, I have the page number where you can find the information. Okay, atoms slips more easily by atoms slip more easily by moving the dislocations through the crystal lattice. That's an answer. I mean, I'm obviously happy with that answer. You could look up more of that. That's the sort of thing that when I talk about we learn about chemistry at uni, that's the sort of stuff I did when I did chemistry at uni. That we can see that there's lots of information, and luckily, thanks to COVID, there's a lot more information than used to be. So because of a lot of unis, well, I mean, this has been up for 10 years, but this is probably a good explanation of what's going on here. The reality is, I just don't know if anyone really needs that level at HSC. So I might actually put this on, as a link onto my Facebook, but I don't know if people need that level of detail at a HSC level. Could help you when you get to uni, but I mean, I'm not a material scientist, so for me that sort of stuff is not of much value. Yeah, we'll put it over here. Just as a reminder of something I need to go back and look at later. Hey, type something in the chat just so I know that there's still someone watching. Okay. Moving on, what is our next question? Describe work hardening. Explain why failure often occurs with excessive work hardening. Now, I know that in my YouTube videos, I did go into this. So this would be in Chapter 2 Materials. Prelim Chapter 2. Hey, thank you, mate. Okay, so in Chapter 2 Materials, I will have spoken about work hardening there. So you can see in this video, I'm talking about the 3/4 method, and here we talk about dislocations. And then once we talk about dislocations, presumably I talk about, I comment on real engineering, I think, or might be Wendover Productions, one of the two of them. And then he talks about work hardening, and we talk about normalizing. In our Facebook, we have things on work hardening. Probably the best picture that relates to that. So if we go to annealing, and we say aloha Neil, you should be down here. No, maybe not. Okay, annealing, aloha Neil. At the bottom of that, I have my definition: cold rolling work hardens and produces elongated or stressed grains. And so this video, which we've now seen many times, property of grains, talks about how we can see that work hardening produces these elongated grains, which produces, makes it harder and stronger. And that's because it's harder to push these dislocations around. Okay, so next we describe work hardening. Okay, we will talk a lot, next year we do more about stress strain curves. We'll talk about how work hardening leaves permanent strain, and when you start adding more and more permanent strain, you do eventually create failure. Okay, why is martensitic steel of little use unless it's tempered? Well, okay, so we've got Neil, and we'll go then to our mate Cora. And Cora is, she has acicular grains, needle-like, very strong, very brittle, unless we temper them. Martensite is a body-centered tetragonal, or BCT, and I think it was James who was like, you always talk about this and you always say how it's never going to be in any of the tests I write, and that's true. It's possible that it could be in HSCs, it just doesn't seem to come up very often, but it seems to be something I talk about a fair bit. Okay, what is, explain the difference between full annealing and process annealing. Okay, I have mentioned this several times in the class. What I say is that process annealing protects the pearlite perfectly, whereas fickle ferrite is affected. So that, I have the page number where you can find that. Page 68, it says full annealing is when it's, process annealing, it's heated to a lower temperature, and this removes stress from the ferrite. Only the ferrite is affected, but the pearlite is protected. And normalizing is when we heat to a higher temperature, but then we cool quickly. This produces finer, elongated grains, and we do that in air. And what does it give us? Harder, stronger, smaller, better, right? They're the grains. So that would be what Kanye and the French brand Daft Punk would be all about. And the French band Air, they probably would have an opinion as well. Okay, explain spherodizing and what it does. Okay, spherodizing is found on page 68. This won't be in any test I write, and certainly not a prelim. Yeah, it's not going to be in any test I write. Spherodizing is after quenching, steel is reheated. So it's like tempering, but it's reheated to about 700 degrees. The cementite forms spheroids, which means things like spheres. An oid means like a sphere, and it's much easier to machine. I have some more details there, but I don't really care about spherodizing, so it's not. I haven't seen it enough in the HSC for me to be worried about it. That's why I say I don't worry about it. If I saw it in, if 2021 has a spherodizing question in the exam, then I'll start to worry. But until then, I'm not going to worry. Okay, explain why a mower blade, which needs to be hard and tough, is not an ideal application for aluminium alloys. Okay, so aluminium generally is considered to be a more brittle material than steel, right? So mower blades need to be sharp, which means they need to be hard, but it also needs to be tough, not brittle, so it does not shatter. Aluminium alloys are typically soft. Yeah, it's hard to say that you can have them both be soft and brittle. That's a bit of a tough one. Aluminium is generally considered to not have the same toughness as steel. If we compared the stress strain curves, I'm going to give you an answer probably a little bit beyond what we needed, but we'll open that up. Stress strain. Aluminium and steel. I'll even type in mild steel. Okay, so here we have the two curves of aluminium and steel. Normally we expect mild steel to have a wobble here, and we think that normally we'd say that the wobble happens at around about 300 megapascals. But you know what, I'm happy to live with this. Now, it's important to remember that we can have really strong aluminium alloys. But when we're talking about aluminium, typically what we're looking at is that steel has a much bigger area under the curve. If I was to colour in underneath this curve, the red crayon would use a lot more than the black crayon. And that's how we measure toughness. So, there we go. Okay, what are we getting? We're doing okay, we've still got some time. Why is martensitic steel of little use unless it's tempered? Yeah, we've done that. Spherodizing, aluminium, interstitial and substitutional solids. Okay, so I've got a picture here. Interstitial solid solution adds additional atoms to the crystal lattice. Ferrite is an example of an iron atom. Okay. What does it say? Well, let me go back to the question, and I won't put in my own words. You can read. So, okay, explain the difference between interstitial and substitutional. Okay, give an example. Okay, that's easy. A substitutional alloy would be steel. Steel is a substitutional alloy where we have mostly iron and we have small amounts, interstitials down here, mostly iron with small amounts of carbon. On the other hand, brass is a substitutional alloy. It has mostly copper, and brass is an alloy with zinc. right? Because the rule of 1Z, where the zinc takes the place of a copper atom in the alloy lattice, or in the crystal lattice. So that's the difference, right? If someone asks me, I don't know if I've never written a question and asked that. I think that's a fair question. I don't think I've seen enough in the HSC to really worry about it, but I think it's a fair question. And certainly, I think it's a very fair question to say, identify which of these materials is an interstitial alloy and which of these is a substitutional alloy. That's, I think, quite fair. Okay. Now, what do we got here? Is recycling important to the engineer? Justify your answer. Well, sadly, I think that if I was to call up engineers I know and I said, would you say recycling is important? They would say, oh, not really, right? Whereas on the other hand, 99% Invisible would say, absolutely, it's important. If we're talking about 100-year timelines, we do have to worry about things like, for instance, everyone by now knows my favorite podcast is the Sand Podcast, right? And we are legitimately worried that we're going to run out of sand to put in our concrete. That is a real, legitimate concern for engineers. Now, whether or not, it's probably not going to happen in my lifetime, but that's something that we do need to consider. And sand is getting more expensive, materials are getting more expensive. I think that mechanical engineers definitely need to be worried about recycling, because more and more consumers are getting upset about the expectation that it's up to the consumer to put away, to recycle. They're starting to put more and more onus on the designer to make sure that they're using recyclable materials. Civil engineers, they use a lot of bitumen, which is 99% of bitumen is reused. It's the most recycled material in the world. But I can see that they would maybe sometimes say that if I could dump the material and not have to pay any more than I would have to recycle it. Like, so for instance, if you have crushed concrete. Crushed concrete can be used as road base in roads. So it goes underneath the bitumen, or goes underneath the bitumen on the roads. And it's an important material. We need that material. There's a finite amount of rocks that is readily available for us to crush up. And if we don't use that, we have to put the concrete in a landfill. Now, the thing is, if a government creates an incentive for us to just throw it in a landfill, but by not taxing that dumping cost, then people are going to dump. They're going to dump, and they're going to say, look, future generations can worry about it. Anyway, the fact is, let's see what the answer I've actually written down here, and what answer I think the HSC would want us to see. Recycling reduces the demand for non-renewable resources. Also, recycling steel and aluminium requires less energy and CO2 emissions than production of raw materials. So this is why, for me, I never chuck out aluminium cans, or almost never. I feel bad about it whenever I throw them in the bin, and it's got to be a pretty dire situation for me to not put it in recycling. Because aluminium is just so much more efficient. It can be recycled so effectively. Steel these days, for engineers, I think that steel is like 80% of all steel, maybe 90% of all steel used in structural applications is recycled steel now. And because it is cost effective to recycle steel. And copper, for instance, without going into specifics, when I've worked on projects, I remember asking the chief of signalling, and I asked him what happens to all the copper, and he says we have a big party at the end where we sell the copper because people want to recycle it. It's important that we recycle the copper. So recycling is definitely important. The problem is when there isn't sufficient incentive for engineers to do the right thing, when they're not being compelled by financial incentives. I think is probably important. I'm just trying to think of the video. It maybe take some finding, but I think it's like Wendover Productions talks about how, no, it was a video on thorium reactors, how pretty much anything can be recycled, but the problem is that we have to worry about the electrical cost. So there's an electrical cost of recycling, there's an electrical cost in sorting. So when we sort our recycling, there's a cost involved. And if we had clean energy, we would recycle everything. If we had nuclear fission, no, we have nuclear fission. If we had fusion, or if we had clean thorium reactors, we would recycle everything. But the fact is, it's just generally not cost effective to recycle most things. Steel and aluminium, bitumen, they're always recycled. There may be even an argument, and this is the one last thing I'll say before I move on, that in that road-based analogy I said that it may actually be, in some situations, it may be cost effective, especially in like a remote location, to leave the crushed concrete somewhere for future generations to use, rather than us to use, because they might have access to much cleaner electricity. So that's a consideration as well, that if we're burning dirty coal, then it makes a lot more sense for us to say, look, it's not cost effective for us to use it now. Recycling it is not necessarily the best option. We're better off saving it and leaving it in a clean stockpile that future generations can access. So that's my thoughts on recycling. Probably more detail than I would go to in any other case. Okay. Way too long for a HSC response, by the way. What does EMF mean? Now, EMF can mean electromagnetic force, right? One of the 4 fundamental forces. But if you see EMF, you should think electromotive force, right? And I stress that the M is for motive, and EMF is voltage, right? So when we see EMF, electromotive force is voltage. You can find that. It's also known as potential difference. You can find out that in page 72. Okay. Oh, find the resistance. Okay, what is the difference between a something in series and parallel? Let's bring that in. I don't really like that answer. It's not a great answer. If I go to Facebook and I go to our albums, on our albums we have, titanium, media, albums. In our albums we have resistance, and we have now talked about how in series, if we have 3 12-ohm resistors, the current that runs through, well, so the total resistance is 36 ohms. If we have 4 12-ohm resistors in parallel, the total resistance is 4 ohms. So, I mean, that's a huge difference. And obviously we're going to get a lot more current running through the circuit. So I think that's the best answer I can give. And then we have some questions which I'm not going to go through here. Find the resistance of copper wire that is this long, and a designer is trying to choose between copper or silver wire and appliance. They're both being 5 mil diameter, but silver conducts better, right? Those, I have answers, right? I've worked out the answers for those things. You can look at them and there's the page numbers that they refer to. Okay, the same with this question on resistance here. Okay, what I want to get to is, how does an induction motor work? Now, I set a task, as everyone had to watch a video on AC motors, and I have an answer here. I'm not going to read out the blue part. I'm going to say an induction motor consists of a rotor and stator. Don't even need to write that, but that's probably a good starting point. When current passes through the stator of a rotating magnetic field, when current passes through the stator of a rotating magnetic field, it's through the stator, comma, a rotating magnetic field is produced, which induces current into the motor. This is Faraday's law. This current interacts with the magnetic field of the stator, which is Lenz's law, and causes the rotor to turn. Yeah, that's fine. I'm happy with that answer. You can read the blue stuff, and there's a video as well that I have talked about many times in Google Classroom. Okay, what does the term impedance mean? Total opposition to current or flow. Okay. List the types of DC motors. What are the advantages and disadvantages of each? There's shunt and series. Series starts well, but it doesn't have as much. Series motors have good torque, but will speed up, potentially damaging the motor. Shunt motors have consistent speed but low torque. Compound motors combine both. And that's it. That's our chapter 2 review questions. Hopefully that was worthwhile. I mean, if people have already done that, hopefully there was some content. I mean, I went to more detail on recycling, and I'll include this link on Dislocations into one of our Google things. If anyone had any questions they wanted to talk to, I might go, now would be the time to ask questions, I guess, but otherwise I'm going to wrap this up in a few minutes. So in the meantime, I'm just going to be sitting here putting some things on Dislocations. I'm going to put this on the picture which says everything is made of atoms, the Dalton and Democritus pictures, which should be down right at the beginning. There we go, Dalton and Democritus, and what we're going to do is close that and hit Dislocations and share. Okay, well, hopefully that was of some value to someone. And with that, I think, just check that I don't have anything else open. I will post the answers to prelim chapter 2 review. Yeah, I mean, that's already due for homework. I might wait a bit before I post that, but I'll definitely post them up soon enough. Okay, and with that, we're done.